Polynomials. We're going to start out pretty basic, pretty easy. We're just going to start out by classifying polynomials and then understanding what we're talking about when we speak of end behaviors. We'll also go over turning points and what it means to identify the increasing and the decreasing portions of a graph. Most of this is not calculating things, so it's not difficult that way. It's just knowing vocabulary and reasoning through a few things. So, first up, classifying polynomial functions. A polynomial function, p of x, blah, 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 wah, wah, wah. Yep, it just looks ugly. Okay, understand though that it is simply telling you that you have a number times x raised to a power plus another number times x raised to the next lower power and on and on and on until you have just a number. Remember that you could have x raised to the 0 power, but since x raised to the 0 power is equal to 1, we just get rid of it, and we have what's called a constant. Okay? Now, so now, looking at p of x, here's a better example, if you will. We have p of x, and remember, p can be any letter. It's just like x is a variable. P is just the name of the function. It could be p, t, h, q, bob, anything you want. P of x is equal to 2x cubed minus 5x squared minus 6x plus 7. These actually have names. We have the cubic term. It's the cubic term because x is being cubed. The minus 5x squared is the quadratic term. And it's the quadratic term because if something is being squared, we call it quadratic. Then minus 6x, that's our linear term. When you have y equals x, you have a line. So this is our linear term. And finally, the plus 7 is a constant term. Now, when you're asked for the lead coefficient, you have to organize your function so that it's in the largest exponent to the smallest exponent. And once that's been done, then you can identify the lead coefficient. The lead coefficient is the number that is being multiplied times the variable with the highest degree. Now, the degree of a polynomial is the largest degree of any term of the polynomial. We're going to just work with polynomials that have a single variable. If you have multivariables, more variables than just one, you simply add all the degrees together of each one of the variables within a term to get the degree. That's just a little side note. We're not going to worry about that here. So onward. Here, a degree of a polynomial is the largest degree of any term of the polynomial. The name assigned to each degree is listed in this table. So notice if you have a degree of 0 or no variable, we call that a constant. Here's an example, 73. 73 is a constant. It has one term, and so it's a monomial, because we can also name things by the number of terms. Okay? So number of term names. If you have 1, it's a monomial. The fact that it's a constant, we would say it's a constant monomial. Now, what happens if we have a degree of 1? Well, notice that we don't have a little 1 next to the x as a superscript, but that's okay, because if something has a degree of 1, we don't list it. We don't write the 1 in there. This is linear. There are 2 terms, so it's a binomial. Could you have a linear monomial? Of course. You could have 17x, 1/2 x, anything like that. That would be, there's just one term, it's monomial. So remember that the number of terms and the degree name are not the same. To some extent, the degree does limit the term names. If you've got a constant, you can only have one term. If you've got a linear, you could have 1 or 2 terms. If you have a quadratic, a degree of 2, x squared. In this case, we have 5x squared. It's a quadratic monomial. Why is it a monomial? Because there's one term. If I did plus 3x, now I have a quadratic binomial. If I did plus 7, I would now have a quadratic trinomial. you have to have at least a quadratic before you could get up to having a trinomial. Finally, we get up to a cubic. The cubic is because the highest degree is 3. It's a trinomial because we have 1, 2, 3 items held together by pluses and minuses. Okay, a term is one or more variables along with numbers that are multiplied together. Next up, we have a quartic. Think of a quart of milk. It's 1/4 quartic. The highest degree is 4. In this case, it's a quartic binomial or a binomial quartic. Doesn't really matter which one you say first. It's a binomial because there's 2 terms. It's a quartic because the highest degree is 4. This last one, negative 2x to the 5th plus 3x to the 4th minus 7x minus 9, is a quintic. It's a quintic. Think quintuplets, 5. The highest degree is 5. There are 4 terms. We don't have a fancy name for 4 terms. We just say it's a polynomial of 4 terms or a polynomial with 4 terms. Okay? You do have to memorize the names. Sorry. Now, a little bit of practice. Write each of the following in standard form, highest exponent to lowest exponent, then classify it according to degree and number of terms. Go ahead and do that, and then come back. Pause the video. Okay, hopefully you paused the video and then it didn't take too long. Check your answers. Most of them are pretty straightforward. However, I did note here, negative 4x plus 2x, you have to combine those. Those are like terms, so you combine them. Likewise, over here, the 3x cubed and the 2x cubed get combined to 5x cubed. The 4x minus 6x is negative 2x. It too gets combined. Okay, once it's combined, exponents highest to lowest, and then you name them. If you're confused, bring your questions in. Now, end behavior. The graph of a polynomial function is both smooth and continuous. Smooth and continuous. By smooth, it means the graph does not contain sharp corners. By continuous, it means the graph does not contain any holes or gaps and can be drawn without lifting a pencil from the paper. So on the left in red, we have a polynomial function. On the right, it's not a polynomial function. It has numerous issues. It's got a sharp point, it's got a gap, and then it's got a little hole. What's one thing that we've been graphing that you know is not a polynomial, but it is a function? Think about it. Think about it. Did you say y equals absolute value of x? Good. This is not a polynomial. It's a V-shaped curve. It's got a sharp corner. It's not smooth. It is continuous, but it's not smooth. All right. Now, use your graphing calculator to complete the following table. Number 1 is done for you as an example. Here, and I'm going to do the graphing calculator down here. Bring it up. Okay. What you're being asked to do is to turn your graphing calculator on. Clear stuff that's there. And simply type these in. So we get x squared minus 2x minus 3. Then when you graph it, okay, it looks like this. Now notice that the degree is 2, highest degree. The lead coefficient is 1. You will also be asked for the end behavior. By end behavior, you're being asked in which direction is each end going. So first, look at this left end. Where is it going? It's continuing up forever. Therefore, I've got the up. Where's the right-hand side of the graph going? It's continuing up forever. Okay? So pause the video and try these. Go ahead and pause it and come back and we'll run through what you should have seen on your calculator. Okay, you're back. Number 2 has a degree of 2 as well. This time, the lead coefficient is -1. And the end behavior here, you should have noticed, was down, down. It looks like this kind of a thing. The next one, y equals 2x cubed minus 3x squared minus 2. It has a degree of 3, a lead coefficient of 2. Now, its end behavior was going down and then up. It looked something like this. This next one, again, the degree is 3, but the end behavior is -1. This one had an end behavior where it went up and then down. When you were looking at it, it made this kind of a shape. This next one has a degree of 4, and the lead coefficient is 1. And this one, you should have noticed that the end behaviors were up, up. The next, number 6, degree is 4, lead coefficient is -1, and the end behaviors were down, down. Finally, number 7, we have a degree of 5, lead coefficient +1, and the end behaviors down, up. Number 8, degree 5, lead coefficient -1, end behaviors up, down. Now at this point, if you were in class, we would have a discussion about what patterns do you see? What do you notice? If you're watching this video, you're sitting there all alone. So I would advise you to pause the video and think about and jot down your ideas about, do you recognize any kind of a pattern? What do you think is the pattern? What do you think we can know moving forward? And then start the video again, and I will simply go through what you should have noticed. Okay, you're back. Now, hopefully, in looking at this data, you will notice that when you have even degrees, 2 and 4, you're going up, up, or down, down, up, up, or down, down. Okay? The end behavior goes in the same direction. On the other hand, odds go in opposite directions. Notice I've got opposite directions. Now, here's the thing. Hopefully you notice that if it's positive and it's even, it's going up. If it's negative and it's even, it's going down. If it's odd and positive, it goes down then up. And notice this little line segment here, it makes a positive slope. You had a positive lead coefficient. If you have a negative lead coefficient, notice the end behavior is down then up, and it makes a little negative sloping line if you attach the endpoints of the arrows. This is what you are supposed to understand, is this pattern. If the degree is even and the sign of the lead coefficient is positive, it's up, up. If the degree is even and the sign of the lead coefficient is negative, then it's down, down. If the degree of the polynomial is odd and the sign of the lead coefficient is positive, it's down, then up. If the degree is odd, the sign of the lead coefficient is negative, then the end behavior of the graph is up, down. Now, I'm also going to show you how these get written on things like the SOLs, because they don't use the little up, up arrows. They would say, for this left one, as x approaches -infinity, because that's on the left, y is approaching infinity. Okay, remember here's your xy graph. So x is approaching -infinity, that means it's on the left. Y is approaching positive infinity, means it's going up. Then as x is approaching positive infinity, y is also approaching positive infinity. Here, as x approaches negative infinity, y is approaching negative infinity. As x approaches positive infinity, y is approaching negative infinity. Again, on the right-hand side, x approaches positive infinity, that means the right side of the graph. X approaches negative infinity, says you're on the left side. Y is positive, you're going up. Y is negative infinity, you're going down. Here, you would have as x goes to negative infinity, y is going to negative infinity. Over here, x is approaching positive infinity, and y is approaching positive infinity. Finally, this last one, x approaches negative infinity, y approaches positive infinity. X approaches positive infinity, y is approaching negative infinity. These are just ways to write it, ways that you've got to be able to understand our answers. Okay, now the arrows are a little bit faster when you're just doing stuff quickly. So what I want you to do is, by inspection, inspection means no calculator, determine the end behavior of the graph of each of the polynomials below. Remember to put the function in standard form before inspecting. Go ahead and do this, okay? And in class, if you were in class, I had people come up to the board and drag the up, down, 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 up arrows underneath each one of these. All right, so go ahead, pause the video, and try it to make sure that you understand. Okay, did you try it? Well, check your answers. We're going to put the puppy dog next to his water bowl and check. And make sure that you have the correct answers. On a couple of these, like right here, notice you had to move the negative x cubed plus x plus 5. You had to put it in standard form. Up here was x to the 5th plus 2x. That really wouldn't, if you didn't do this, it wouldn't necessarily mess you up because they're both odd and positive. This one down here might cause you a little bit of issue. Did you get it? Great. Now you've got end behavior. And end behavior, recognizing what the end behavior of a graph is supposed to look like, will very quickly help you to understand which graphs could possibly represent your polynomial function and which graphs absolutely cannot. Now, turning points. A turning point is any point where the graph of the polynomial function changes from increasing to decreasing, or decreasing to increasing. So, increasing, there's increasing, there's decreasing. A polynomial function of degree n greater than or equal to 1 has at most n minus 1 turning points. It might not have any turning points, okay, if it's odd, but at most it can have one less than the degree. A polynomial function with an odd degree polynomial functions with an odd degree have an even number of turning points, while polynomial functions with even degrees have an odd number of turning points. Okay? So here, notice there are no turning points. It's increasing all the way. Here, there are two turning points, here and here. For this one, we can say that it is decreasing from negative infinity until negative 1, and then from 1 to positive infinity. Over what values of x is this thing decreasing? It's decreasing here and here. That would be from 1 to positive infinity and from negative infinity to negative 1. Now, this graph is increasing over the values of x from negative 1 to 1. From here to here, it's increasing. Now, why do we just use parentheses and we don't use the brackets? Because at the turning point, it's ending. It's changing from decreasing to increasing, so it's not doing one or the other. Okay? So since it's the turning point and it's not increasing or decreasing at that point, it's changing directions. It stays as a parenthesis. Okay? Now, if you'll turn past your notes, you'll see polynomial functions, some work you're going to do, and then the next page says end behaviors, and then you'll see where it says turning points. Okay? I want to go through this first part with you to make sure you understand, because it's important to have all of this down. The points at which a polynomial function switches direction is the turning point or points. If the turning point is higher than any nearby point, it is called a relative maximum. It might not be the ultimate maximum of the graph, but relative to the points right around it, it's the maximum. If the turning point is lower than any nearby point, it is called the relative minimum. Maximum and minimum values are called extrema. Turning points define where the function is increasing or decreasing. If a function has no turning points, then the entire function from negative infinity to positive infinity is increasing or decreasing depending on the direction it's moving. You're talking about increasing and decreasing. You're asking over what values of x is the function doing this. Now, using the calculator to find your turning points, we have this crazy thing here. X cubed minus 6x squared plus 7x plus 2. So let's bring up our calculator. And we're going to put them right over here. And we're going to go to y equals, and we're going to put this function in. So we're going to put in x. When you raise this up to cube it, don't forget to arrow over, if yours doesn't automatically, to drop it back down again. Minus 6x. I use this squared because then it just keeps it dropped down. I don't have to worry about making some crazy big exponent accidentally. Plus 7x plus 2. Press enter, and then we graph. Now I can see I've got 2 turning points. I want to move the cursor to the left bound of the turning point, hit enter, the right bound, hit enter twice. But first I have to use the calculators right here. So second trace will get me to the calculate. I'm looking for, let's first do the maximum. So we'll do the maximum first. See where the cursor is to the left of the maximum? So I just press enter. Then I'm going to move it along the curve until it goes past the maximum and is to the right of the maximum, and I press enter. And then for the guess, I just press enter again. And this tells me that my relative maximum is it's positive, is at 0.70900 blah, blah, blah. All right, so right now I really just care about the x value. So I'm at 0.709. 709. I'm not going to worry about what the x is, okay? Actually, I guess I should, since I'm just being asked for the x. Have to bring it back. 4.303. 4.303. So there's my relative maximum. My relative minimum I'm going to find in a similar fashion. I'm going to do second trace, which will get me to the calc menu. Then I'm going to come down here to minimum, and I'm going to press enter. Now I'm going to move the cursor so it's a little closer. Here it's to the left of the minimum that I want. I press enter, and I'm going to make it go to the right and press enter. And then guess is just press enter again. And this is 3.29 and negative 4.303. Okay, so 3.291, 3.291, and negative 4.303. Now, if you're asked for the relative maximum and relative minimum, that's where they're at. They're not extrema. Why are they not extrema? Because this actually keeps going up forever and down forever, so the absolute maximum is infinity, the absolute minimum is negative infinity. These are just relative ones. Now, notice that the curve is increasing, 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 hits here, and then it's decrease, 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 here, increase, 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 increase. So my curve goes like this. I hit my maximum first. My increasing interval or intervals, I have two that are increasing. It's from negative infinity until I get to 0.709, and then it starts up again at 3.291 and keeps going to positive infinity. The decreasing interval is this section here, and that's from 0.709 to 4.303. Oh, no, I'm sorry. I'm reading the wrong. It's 3.291. Now, when you're asked about increasing and decreasing intervals, what you're being asked is over what values of x is y increasing / decreasing. Okay, when you're asked for those increasing and decreasing intervals, rewrite this out next to it. Over what values of x? So yes, you're looking where y maxes or mins, but you're asking over what values of x from left to right. Oops. To right. And you could have more than one increasing, more than one decreasing. If it's not increasing or decreasing, it's constant. Okay? Wait, here's an example of one. We have negative x cubed plus 3x squared. Well, it's a cubic. Since it's a cubic, I immediately know my domain is negative infinity to positive infinity, and I know my range is negative infinity to positive infinity. If it's an even number, if it's an even degree, then it's going up, up, or down, down. Ooh, then I'm going to have, domain will be negative infinity to positive infinity, but the range will have either a minimum or a maximum. Now, I need to find the relative maximum and the relative minimum. I could do it using my calculator like this again, or I could use Desmos. Since you can use Desmos on the SOL, I'm just going to do a quick, remember, y equals, and we'll put the equation in here. So you can do negative x cubed, arrow over, plus 3x squared, and then we could graph it. And here's your graph. Okay, this is what it looks like. If you want to see it up higher, you could change your window and say, I need to go higher on the y value, so I'm going to go to 20, and I'm going to make each one of these by 2. And so now I can graph it again. And there we go. So now I can see it. Okay? And it doesn't look like there are any. It looks like it doesn't have a maximum or a minimum. Now, you can zoom in, you can calculate, okay, and zoom into this little area and see if this is lower and this is higher, or does it just make a smooth move through. If you want to, you can do window. Oops, no, sorry, you can do zoom. The easiest way to check things out is zoom box. It puts a little cursor here, so I can go up a little bit and over here to the left. I can hit enter. Then I can go to the right. See how it's drawing my little box? I can go up. I can say, I just want to see that. And now it's going to blow it up on the screen. Notice it just keeps going down. There's no maximum or minimum. So in this case, there would be none. I want to show you on Desmos how to put this into Desmos. Let me pause the video and just go to get it up. Okay, so negative x cubed plus 3x squared. y equals, oops, y equals negative x cubed plus 3x. Oops, that's not it. That can't be it. What did I just? Negative x cubed plus 3x squared. Plus 3x squared. Then okay. Negative x cubed plus negative x cubed plus 3x squared looks like this. What did I do different here? Oh, look at that. And if I were in class, somebody would tell me that I forgot to get the x there, and then I can graph it, and I can actually do zoom, zoom, standard will get me back. There we go. Now I have a minimum and a maximum. Okay, so I had typed it into the calculator incorrectly, which you're less likely to do if you've got a real calculator. This one on the screen sometimes doesn't pick up things when I click on it. All right, so either one of these, if I want maximums and minimums, notice that I have points here already. 0, 0, 2, 4. Great. So I have 0, 0, and then 2, 4 are my points, and this guy right here is increasing. So 0, 0, and 2, 4 are my extrema. So it's at 0, 0, and then at 2, 1, 2, 3, 4, and it goes like this. So now my relative maximum is 2, 4. My relative minimum is 0, 0. The end behavior as x approaches positive infinity, that's this guy over here. Y is approaching negative infinity. As x approaches negative infinity, that's this side, what is y doing? He's approaching positive infinity. My increasing intervals, that's where y is going up, left to right. The x values over which that occurs are from 0 to 2. On the other hand, I have decreasing intervals. Here y is decreasing and y is decreasing left to right. But over what values of x? Well, from negative infinity up to 0, then it starts increasing. Then at 2, it starts decreasing again and keeps decreasing till positive infinity. This is how you are to continue working on the other problems. You have 1, 2, 3 more of those to do to practice. Okay? And then you've got some other practice with your exponent rules from Algebra 1 and your naming. It looks like a lot of work, but especially the naming part, that goes lickety-split. Okay? Now, in summary, polynomials are named by degree and number of terms. Constant, linear, quadratic, cubic, quartic, quintic. Yes, you have to know those. Monomial, binomial, trinomial. Yes, you have to know those. Now, end behavior, when it's even and positive, up, up. When it's even and negative, even being the degree, it's down, down. Odd, positive, down, up. Odd, negative, up, down. The even ones are easy to remember. The odd ones can be too if you just connect the arrow points. I have a positive slope or a negative slope. Okay? And it goes with the lead of the sun, the sign of the lead coefficient. Differences can be used to determine the degree of polynomial. This is actually, that's left over from what was in your book, which is really not an objective, and nobody really would use that. Okay? At least not at this level. That's it.